Welcome to everybody. Here come back to our promise yesterday in an exercise related to the stress bending distribution along a beam. My reference book is Aircraft Structures TAG Magson. That is a book related to aerospace engineering, but in this case the concept is equal to the civil engineering, structural engineering. So here no airplane is called as example, but we stay talking about of a simple beam. In this case, a E-shaped beam. We can see the exercise is the 16.1 of the Maxon. We can see that this beam is a E-shaped beam, as I said before, and we have a two flange, the first flange, the second flange, and this is the web. So for the Italian user, I translate this stuff. So this is for the Italian users ala superiore ed ala inferiore, e quella che in inglese viene chiamata web noi la indichiamo come anima. So flange, web, flange, upper flange, bottom flange, web. So I in this exercise try to translate for the Italian users because I don't know if everyone know the technical notation expressed in English language. So we have this beam. Our scope is to determine the bending stress distribution due to the moment applied around the x-axis of about minus 100 kilonewton per meter. So times meter. So we can see here I drew some stuff. As first thing, we call the dimension of 300 millimeter as A, the dimension of 200 millimeter as B, the thickness of the flange, upper flange, bottom flange as equal to 20 millimeters, and the web thickness indicated with WT is equal to 25 millimeters. Data are summarized here in this red block. You can see also G1, G2, G3. This is the center of gravity of single rectangular shape. So this first rectangular shape, second rectangular shape, and third rectangular shape. We can derive these G1, G2, G3 as the first one is B divided by 2 in X coordinate, because this is this quantity. I can put a reference frame. Here's the arrow because I don't need anymore. This is our reference frame, initial reference frame of Y initial, X initial. Y, the other reference frame, Y and the X in this case need to be used after. If I start from here, this is clearly B over 2. And this is the xg of the G1. The other coordinate is Y, coordinate of this G1, that clearly is this quantity. So this arrow is A. If you can see, this is the half thickness of the upper flange. This is this dimension. Let's say let's do in blue, for example. This is T divided by 2. So if I make this calculus, A minus this quantity, the half thickness of upper flange, that is the equal of the bottom flange in this case, I obtain the coordinate yg1. So this is xj1, xg1, and this is yg1. So numerically we have xg equals 100 millimeters and yg1 equals to 290 millimeters. So 0.1 meter and 0.29 meter. The consideration for G2 and G3 is similar. So we can see the other coordinate, but it's simple. I show you for a complete explanation, but it's simple to calculate the G1, G2, G3 at this level. G2 is equal in xg2 b over 2, because if you look, G2 is placed here, just here, and this is this coordinate, b over 2, G2, on the x axis. Instead, for y coordinate, we have a minus 2 times the thickness of the flange divided by 2, all these divided by 2, plus the thickness of the flange, because this is always a, our beam height in this case. So this is T and this is T. If I make the difference between A, all this dimension, minus 2 times T and T1, T2, but T1, T2 is similar, is equal values, I obtain this distance. But the rectangular shape that contain G2, the centroid G2, in y direction is at half of this 8. So this quantity here is equal to A minus T1 plus T2, but T1 and T2 are equal, so A minus 2 times T, divide by 2, because this is the half part of this 8 that we obtain with the previous calculus. So, but we obtain the half 8 of this quantity here. The 8 obtained before, this is half 8, but I must refer with respect to the x inertial axis, so I must add this other quantity. So the xg2 is all this quantity. So this is a minus 2 times t over 2 plus the thickness of the bottom flange. So the coordinates 100 millimeters and 150 millimeters. To G3, I have simply b over 2 for xg3, that is this distance. This is b over 2, clearly. And the xg3 is the half thickness of the bottom flange, but again, the upper flange as well as the bottom flange has the same values of thickness, that is equal to 20 millimeters. How you can see. So this is t over 2 as a coordinate of yg3. So we have 100 millimeters as xg3, and as yg3 we have 10 millimeters, that is the half part of 20 millimeters. So here on the right side we have, in this box if you want, we have the calculation of the A1, A2, A3. This is the three area of the three rectangular shapes. The first one is simple because the first rectangular shape is this. Clearly this is the second, this is the third. The first one is B times T. Simple formula for the rectangular shape. A2 is equal to A minus 2 times T. All this quantity enclosed in curved bracket is multiplied for WT, that is the web thickness. Clearly, because we said before that this all the height of this third rectangular shape, and this is the height, and the base of these rectangular shapes, that is equal clearly to the web thickness. The last area, A3, is equal to A1 because the bottom flange, this flange, is equal to the upper flange. So we can note from these few things that this beam is 2 times symmetrical. So what means? Is symmetrical with respect to y-axis, and is symmetrical respect with this axis, that is x-axis, that we're going to see effectively this explanation, that is a neutral axis. X-axis is the neutral axis. Well, so this structure, this E-shaped beam, is 2 times symmetrical. It's symmetrical with respect to y direction, as it's symmetrical with respect to the x direction, that is for us the neutral axis. We can calculate now the coordinate of the centroid of whole beam, xg and yg. In English we can call this xcg and ycg, center of gravity is the translation. So we can calculate as the xg1 times a1 plus xg2 times a2 plus xg3 times a3 divided by the summation to n1 to third area of an. So the summation of all area that we have in this shape, in this beam. So the numerator of this fraction is that we in Italian call momento statico. This is all momento statico. But in English we say the first moment of area of the cross section. In this case the cross section is the E-shaped beam. So English is first moment of area, Italian is momento statico. This is the summation of all momento statico, or first moment of area of cross section, divided by the summation of all area that we have in this beam. If you make this calculus, you obtain exactly this number, that is this value, that is 100 millimeter is equal to 0.1 meter, and clearly is the how we expect is the half part of the length of the flange, b over 2 is exactly 100 millimeter. For ycg, the y coordinate of centroid of whole beam is equal exactly as before, summation of all momento statico, or all first moment of area of cross section in y direction, divided by the summation of all the area that we have in this beam. And clearly also here the result is that we expect, because is equal to 150 millimeter, that is exactly the half part of the height of whole beam. So we have reached in this case that y and x reference, so y is this and x is this, are exactly the centroidal axis, and C is the centroid of this beam. So C2 is also coincident with CG. The centroid of the second rectangular shape is coincident with the CZ of whole beam. So in this case we have also demonstrated that this beam is 2 times symmetrical, because the y-axis divide exactly the beam in 2 mirrored shape, the first one and second one, left and right, and x cut exactly the beam in 2 equal parts, upper and lower part, or upper and bottom part, as you want to say. We have reached two important results. The first one is this: the y and x is centroidal axis. The centroid of this, the axis through the centroid are also two symmetrical axes, so the beam is 2 times symmetrical with respect to y direction and with respect to x direction. Now we move on to calculate the moment of inertia. This is equal, fortunately for Italian user, for English user, moment of inertia, but with respect to with respect to x-axis. So we know that we have divided this beam in 3 rectangular shapes. The two highlighted in black are the 2 flanges that have equals dimensions. That one highlighted in blue pen with the blue pen is the web, clearly, of the our beam. Ixx1, the first moment of inertia of this quantity of this first rectangular shape here, where is written G1 is calculated as B times T at third power divided by 12. This is the moment of inertia of this rectangular shape with respect its own centroidal axis, that is this axis here. Okay, but now we can transport this moment to this CG. So we want to calculate the moment of inertia with respect to this axis, x-axis. In this case, we apply the theorem of the parallel axis for the moment of inertia, or Huygens-Steiner theorem at our latitude, but everywhere I joking, is also known as Huygens-Steiner theorem. So this is the moment of inertia with respect to its centroidal axis through to the centroid of centroids G1, plus the area of the first rectangular shape times the distance at the square. This distance is D1, is the distance that is the distance between the G1 and centroid C. That is also the CG. Sorry, here is a CG, center of gravity of wool beam. So, see, this is E with respect to the xg1 plus the transport moment that I indicate A1 times D at square. So, this quantity is clearly B is the base of the flange, that is this quantity, times T at third power is the height of the first flange, this quantity, T, is also here, right also here, times the area is B times T, times the distance D1 is calculated as follows. A is the height of wool beam, okay? So the distance from the G1 to the CG is this. Is quantity, and this is exactly A over 2. I can write this in another color. This is D1, let's say orange color. This distance here in orange is A, this distance is A divided by 2. So if I make A divided by 2 minus T divided by 2, I obtain exactly this distance here, that is the distance D1. A divided by 2 minus T divided by 2 at square power. I can write this as a numerator A minus T divide all the numerator by 2. At square power we obtain a xx1, the moment of inertia of the first rectangular shape, that is equal to this stuff, so 7.85 times 10 at 7th power of millimeter at 4 power. This is a moment of inertia, okay? The measure of the unit of measure of a moment of inertia. Clearly, the xx1 is equal to xx3 because the two flange, upper and lower flange, is equal. So, because you see here, this value is reported also here because the two flanges are equal in dimension, and here the distance is at the square. So also if the distance here is negative, but is D1, D2 is at the square power, becomes positive. So the final result is that Ixx3, the moment of inertia of third rectangular shape, is equal to moment of inertia of first rectangular shape. For the Ixx2, the moment of inertia of this rectangular shape, we can calculate, as you can see, as the base is Wt, that is the thickness of the web, times, sorry, here we have a blue pen, times the height of this web, that is a minus 2 times t at third power. We have obtained this value before when I explained the coordinate for the ymg2 divided by 12, because here you don't see any transport moment, because this rectangular shape has a here centroid coincident with CG. So clearly the moment of inertia with respect to x-axis is exactly the moment of inertia of this rectangular shape with respect is its own centroidal x-axis. So this quantity is equal to 3.67 times 10 to the 7th power millimeter at 4 power. So all these to say that the total moment of inertia Ixx is equal to 2 times Ixx1, because these and these are equal, plus Ixx2, that is equal to 193.7 times 10 at 6 power millimeter at 4 power. This is the moment of inertia of wool E-shaped beam with respect to x-axis. Now move on to calculate the stress distribution. The moment applied at this beam is M, that is minus 100 kilonewton times meter. So if you see the moment from this point of view, the moment appears to be clockwise. So the bottom flange is in tension. The fiber placed here in the y negative direction are in tension, and all the fiber in the y positive direction are compressed. So if you I make a 3D draw, clearly the movement is so. Okay, if you see this 3D draw, this is in tension, this is in compression, so it's bent to as a sandwich in this case. If the moment is negative, we have the formula that have been studied in the last lecture. We have moment applied times y1 divided by moment of inertia. Y1 in this case is exactly the distance from CG to the upper flange, and that is 150 millimeters, exactly the half part of the length of the wool beam, and we have exactly this. So the stresses due to the bending is equal to minus 77.44 Newton over millimeter at square. The sigma Z2, that is the distribution of the bending stress at the lower flange, is the opposite of the sigma Z1, that is equal, so if the first one is negative, the second one is positive. 77.44 Newton over millimeter square. So here we have the diagram of the distribution of the bending stress. We can note that in the upper flange has a negative stress of this value and varies linearly through the height of the beam, and we can note that at C, in centroid of the wool beam, we have 0 Newton over millimeter square. So that indicates us that this axis is neutral axis, because here sigma Z is equal to 0. And we said in the last lecture that the neutral axis and the neutral plane are two places where the stresses and strains are equal to 0. So in this case we can note this. So we can say clearly that x-axis in this case is not also a symmetrical axis for the beam, but is also a neutral axis for this beam, because the stresses due to bending moment is equal to 0 here. In the lower flange at bottom, we can see the same value of obtained for the upper flange, but the stresses here are positive. We have this value of 77.4490 Newton of millimeter squares. So this is a simple exercise to apply the formula studied in the lecture presented yesterday. In the next exercise, we'll complicate a little bit the exercise, introducing a moment that is have a certain angle with respect to vertical, let's say vertical axis, in this case represented by y-axis. So, but for at first at moment, this is exercise can be useful to us and to you for understanding how to apply this simple formula to calculate the bending stress that is acting on the beam, in this case on the flange, upper flange and lower flange. Why we have all these diagram? Because the moment is clearly applied in the vertical plane. So this is the vertical plane. In the next exercise, how I said before, the moment has an inclination with respect to this plane. So we have the combination of two moments: the moment applied in the vertical plane and the moment applied in the horizontal plane. Here the moment as let's say this is a b vector of the moment, is applied only here, only in this vertical plane. So we have only one moment, that is the moment around the x-axis. So the moment around the y-axis is equal to 0. Clearly you can see from the figure. In the exercise, the next exercise, we see the combination. So we'll see this formulation: sigma zeta xy is equal to mx times y over xx plus my times x divided by iyy. So we can calculate, we must calculate also the moment of inertia with respect to y-axis. So this is the combination, this quantity is the combination of two moments, and we obtain clearly a distribution of the bending stress at certain point indicated from the coordinate x and y. If I want to obtain only the distribution along the height of the beam, I must put this sigma z x as equal to 0 and y at certain value of y. So in this case I obtain exactly this diagram, but in the next exercise all these will be clarified accurately. So the videos can be stopped here. I hope this exercise can be useful to everybody to understand this formulation, and we will see to the next video. Bye.